with our November 21 HL Physics question paper 2, and here we're looking at question 8. Okay, as usual, we've got the paper, we've got the mark scheme, and we've got our data booklet if we need it. Okay, now this question is clearly about Doppler effects, so I'm just going to scroll through and try and find the Doppler. There we go. Always good to be ready with it. Okay, let's get started. We're firstly asked to state what's meant by the Doppler effect. Okay, and hopefully we're fairly okay with this. It's an apparent change, okay? It's a change in observed frequency as stated in the mark scheme. Okay, frequency or wavelength of a wave, for example, sound or light, due to the relative motion of an observer and a source. Okay, all right, so in this case I'd say I've got both the marks there. Just a quick point here, all right, do not award MP1 if they refer to wavelength. This is a little bit nasty. Okay, in my opinion, what I would say here is you're expecting the word frequency. I've said frequency or wavelength. This would get the marks here, okay? So don't worry about it. Okay, it's just one of those small points. People like to refer to frequencies here, mainly because it's the frequency that we process, not the wavelength, okay? We're not going to lose too much sleep over that mark, all right? But I would stay with the term frequency where possible. Now, we're told a plate performs simple harmonic oscillations with a frequency 39 Hertz. Funny choice of number here. Why they didn't choose 40, I'm not sure. And an amplitude of 8 centimeters. Now notice here 8 is given in centimeters. You're going to have to do some conversion because in the next question you're asked to show that the maximum speed is about 20 meters per second. Now, if we have a quick look at the mark scheme, they go straight in with use of 2 pi times f times a. Now that's not what I've done. Okay, I've gone out and dug out the equation for speed. Now this may be overkill, okay, but you'll see it there in your data booklet. And the reason I'm doing this is because sometimes I find that these mark schemes, they don't always give you where everything's from, and you may be wondering where that is. I mean, I personally don't remember seeing that equation on a mark scheme. Okay, you may not know where that's come from. Let's have a look at where it is. You're asked to calculate the maximum speed. Now, as we know, when we're doing simple harmonic motion, the maximum speed becomes in the equilibrium point, i.e. when x is equal to 0. Think of a pendulum swinging. Think of a mass on a spring. Both of them are fastest when at their equilibrium point. Now, why is that important? Well, we can put it into our equation. We've got omega times the square root of x0 squared, so that's the amplitude squared, minus x squared. We're going to take away 0, and so therefore we just ignore x squared, basically. We've got 2 pi f times the square root of x0, which is 2 pi f times x0. And then we're going to put our values in. We know f, we know x0, and we've got a value of 19.6, which I'm sure you'll agree is very close to 20 meters per second. So far so good. All right, I'm going to be honest with you guys. I didn't like this next question, and you can see here I got frustrated. I got the wrong answer, okay? When I do these videos, I don't like to do them with the mark scheme in front of me. I like to put them in myself in your position to show the mistakes perhaps that you can relate to, but then think about what that really means for you guys and how important it is, okay? So you'll notice here, the issue comes with this question. Comes with the fact we've got sound being emitted from a stationary source towards the oscillating plate. Okay, the speed of sound is 340 meters per second. Now, what clearly lots of students do, and what I did as well, is that I assumed that our Doppler only applies once here. Okay, I think when I was reading, I didn't read the question carefully enough. And so what I assumed was that we've got the moving source, okay, and we're going to calculate our maximum frequency by looking at our equation. Okay, so let me just get this up here. There we go. All right, I decided to using moving source, and I went for v over v minus us. That will give me the maximum value. Okay, and so a lot of people will be there, okay, getting 2,550 hertz. That's obviously not what the answer is. Okay, the answer here is about 2,700. Okay, before we go on and look at what the actual answer is, notice here, however, that that's still getting you a mark. All right, I'm not too upset about this. Okay, I missed the fact that actually we need to apply Doppler twice. Why? Well, at one point we're emitting the sound, okay, at our oscillating plate, okay, and it's going to be reflected back, okay, and so effectively Doppler has to be applied twice. We can determine the frequency at the plate, okay, and that is going to be the frequency that we would observe if we were at the plate, okay. That maximum frequency received by the plate is going to be 2,400 times the sum here, so we're actually using this second equation here, okay. Effectively, according to if we were at the plate, the source is moving here, okay, and then it's going to again get re-emitted, so that higher frequency 2538 is then going to get re-emitted to our source due to in this reflection process, and then therefore it's going to become amplified again or increased again, this time according to the moving source formula, which is the top one here. Okay, the reason I'm rushing through this is because I think this is one of those things that many students wouldn't pick up, and you can notice that in the mark scheme where they offer some alternative marks for simply getting the question wrong, like I've done, okay, and I'm sure many of you guys have as well, okay, is because it's quite often very hard to process and hard to put together. The reassuring thing I would say at this stage is there's only one mark here, okay? As long as you've done that point of assuming that we apply Doppler once, you'll still get a mark for your work, and then 1 mark for this question is more than enough. I wouldn't worry about it. Okay. The next bit is part D, and it suddenly goes into looking at some diffraction. Okay, now on the surface of this, I think students find these quite stressful, these kind of graphs. However, you're only being asked 3 questions, okay? Now, on the graph, we can see the primary and the secondary maxima. We've got 4 parallel slits, so we're passing our light through the 4 parallel slits, and we're then told that the number of slits is going to increase, but their separation and width stay the same. So some things are going to change here and some things are going to stay the same. Okay, now we're asked firstly about the angular position. Now my fairly basic and boring drawing is just on the top here. Okay, now remember that if we want our constructive interference to happen, we need to have n lambda equal to d sine theta. That's our constructive interference, and in this, n is not the number of slits. That's often something that gets confusing here. N here is the order of the maxima. Okay, you'll notice here this has no dependence on the number of slits, and so actually the angle theta is going to be exactly the same provided the separation and width stay the same. And so the angle itself is also going to stay the same. We're going to have n is constant, lambda, d all constant, therefore theta as well is constant. So changing the number of slits does not affect the angle at which we'll observe this. However, what it does do is makes our diffraction pattern much more defined. Now, those of you who have done this in class, you may have used a diffraction grating, which is many slits. Okay, what you'll notice is those diffraction patterns are much better defined, much clearer. And the reason that they're more defined is actually linked to those parts 2 and 3. Okay, by becoming more defined, really what we're doing is we're making it this condition, n lambda equal d sine theta, much more kind of exclusive. Those positions at which the maxima are achieved are becoming more and more unique. In other words, in between those maxima, the waves are cancelling each other out more and more and more. By virtue of that, our primary maxima are going to get brighter, and our secondary maxima are going to get less intense. Okay, and our primary maxima, I should say as well, are also going to get a lot narrower. Okay, so we go from a broadly spread out shape to one which is very finely pointed but still crucially at the same position, as indicated by part 1. So you can see it this way, that if you add more slits, you are directing the light more coherently to those maxima, and in doing so, you're cancelling out all the bits in between. And the result of that is that your peaks are going to get thinner, and those secondary maxima are going to get duller and duller until effectively they're cancelled out, and we have a really well-defined diffraction pattern, as in a diffraction grating. Okay, again, a lot to go through there. Okay, you're not expected to explain these things. So again, if you're really feeling a bit lost, okay, in these kind of questions, there's 3 options, right? There's stay the same, there's decreases and increases. Please don't leave these questions blank. Try and think about the physics, but if you're in a rush, and I know it's stressful, have a go. Okay, you've got some understanding there. It's not a guess, it's an educated one, and it's one which you can make some progress with. Okay, please do let me know if there's anything which is unclear.